as Peter said, I work at the RESEDA, which is spin echo spectrometer. And yeah, I will tell you a bit about the spin echo techniques in general. First, I wanted to show you some nice pictures of Munich, since most of you can unfortunately not be here. But well, we might rearrange this at some point. And as we learned only recently, for example, the European Conference on Neutron Scattering will actually be in Garching in 2023. So until then, we hopefully will have time to meet, but otherwise this would be a good occasion as well. And well, you've seen already quite a few pictures already of our facilities. Our director showed you us the nice overview over the reactor, where you can see like the old atom egg, as it's called, and our new reactor. We have here a nice picture of our reactor pool, which I always think is a pretty cool thing to see. And we also have here the experimental hall, where we have instruments like, for example, Panda that Astrid was talking about. And this is the Neutron Guide Hall. And I think Sebastian already showed this picture, where you can see in magenta SANS 1, and right next to it is actually RESEDA. You can basically see here like this blue crane that we are using. Anyways, so I'm going to give you a quick overview about what I will talk about. And I will give first an introduction about some basics about neutron spin echo, because it's a somewhat more exotic technique and not everyone might know the basics. And after that, I will give you 2 science cases that we measured at RESEDA using the MIEZE technique. And actually, I'm quite happy that Astrid already talked about iron, so you can see this material from 2 very different points of view. So it's actually really nice to have these comparisons. Now, first, because I said there's a lot of spin echo techniques, and there's a big zoo of spin echo machines, even though you might not have heard of it. The technique is actually rather young. It's from 1972. And I will not talk about all these techniques because it would just take way too much time. But I will be talking about the classical spin echo and about the resonant neutron spin echo, especially in the longitudinal configuration, and then as well about the MIEZE technique. There's, of course, you can also combine neutron spin echo techniques with triple axis techniques that Astrid talked about, and there's an instrument at the FRM2, one in Berlin, which will actually be moved to FRM2, and another one at ILL. And but I will not be talking about those because it's not quite my expertise, to be honest. So let's start with some very basic properties of the neutron we need to know to talk about spin echo. So first of all, it's the Larmor precession of a neutron in a magnetic field. Yeah, what you might know is that when you put a neutron in a magnetic field, it might start to precess depending on the direction of the magnetic field. And the spin actually starts to precess with the Larmor frequency of the neutron, which only depends on the gyromagnetic ratio and the applied magnetic field. Now, this Larmor precession can be used to flip the neutron spin by a specific amount. And the angle with which we can flip the neutron with using a magnetic field depends on, again, the gyromagnetic ratio, the applied magnetic field, the neutron mass, the Planck's constant, and the thickness of the spin flipper. And for example, we can, like this, determine, okay, how big a field do I need to flip a neutron that has a specific wavelength, because this strongly depends on the wavelength of the neutron, by, for example, half a pi or by pi. And I will start now with introducing the classical neutron spin echo technique, which is, it was invented basically in 1972. And the classical setup looks rather simple as a sketch, but is much more complicated, as we will later see. So spin echo, we work with polarized neutrons. So we want all our spins to point in one direction. You can see here below the sketch is actually the direction the spins point in. And the direction. Anyways, so we have the neutrons coming in and we polarize them, so their spins all point in the same direction. And since we do not want to lose neutrons, we have always a small magnetic field along our instrument to basically keep the neutrons on their path. Because there's always some small magnetic fields that you might have from a neighboring instrument, or even the Earth magnetic fields that might disturb our neutrons. So we have a small magnetic field just along the entire instrument. And after the polarizer, the spin of the neutron actually slowly adiabatically tilts into the magnetic field, into this guide field. Now, we want to start the precession at a very exact moment. This is why we have here a pi flipper. So you can see here in blue, we have here first the messy neutrons, then polarized neutrons, and then they're tilted into the field. And with this pi flipper, we actually flip them abruptly to have their spin pointing upwards. And this field applied in the solenoid actually points perpendicular to it, so the neutrons will start precess. And the precession frequency here, the precession angle, sorry, that a neutron gathers here depends on its speed, which is directly proportional to its wavelength, and the length of the solenoid and the applied field, and again, our gyromagnetic ratio. Now, if we have no sample in here, we have like a neutron spin. If we just look at one neutron that rotates and rotates and rotates like a clock that we're winding up. And at the end, we have a specific phase. If there's no sample at all, and we reach the second solenoid where the field is actually applied in the opposite direction, the neutron will wind down again. And we will have the same neutron at the detector as we had when we started in. But of course, if the sample interacts with this, if the neutron interacts with the sample, the speed of the neutron will change, and so the time it spends in the magnetic field will change, and it will have done a different number of turns. And this is the polarization that we measure in the end using spin echo. You will see this on the next slide. But I wanted to still point out that this phase that the neutron gathers is actually can be written as the frequency times a bunch of numbers that look kind of messy now, which we defined as the spin echo time. You can see this basically depends again on fundamental constants such as h bar, the gyromagnetic ratio, the mass of the neutron, as well as its speed or wavelength, and the magnetic field and the length of the coil. And you can see that the wavelength, or rather the speed, are really important here because it comes in with a power of 3. Now, what we usually do in spin echo is that we assume we're at either in an elastic or in a quasi-elastic scattering regime, not as Astrid mentioned before, the inelastic scattering regime, where we assume that the difference of the neutron of the speed before the sample and after the sample is rather small. And as I said, we measure here a polarization, which is actually the Fourier transform of the S of Q and omega, which is what you would usually measure, for example, with a triple axis instrument or a time of flight instrument, and which is usually a measure that is much more well known to the general community. So that's why I put this here, so that if you are actually familiar with those sort of numbers, that you know what the context is here. Now, there's a small problem with the classical NSE machines, is that to go to higher spin echo times, you need bigger magnetic fields, and so you need bigger coils. And those get really, and if a coil gets really big at some point, you can see here in this image that there's inhomogeneities at the edges of the coil, which is very difficult to avoid unless you add much more complex system of coils to balance this out. So, and this inhomogeneity here of the field integrals depends on the size of the coil. So eventually it will become really difficult to make bigger and bigger coils. Now, some people solve this problem, like for example, the JNSE at FRM2, by starting to use superconducting coils, where you can usually produce larger magnetic fields with smaller coils. So this is one way of working with it. And one of the other issues you have with spin echo, with the classical spin echo, is that, well, as I said, if you don't have a small magnetic field all along our instrument, we will start losing neutrons, or rather neutron polarization. Their spin might get distracted by something that is nearby. And so we always need to have a minimum field here. And this is of course a problem, because if we want to get to really, really low times, so to shorter times, we would need even shorter fields. But well, there's only a minimum field we can apply before we lose our neutrons. Because of these two issues, the neutron resonant spin echo was invented, basically. So these big solenoids are replaced by resonant spin flippers, which give them better field homogeneity. And it's actually that the angle that you produce with the NRSE is twice the angle that you get with the normal NSE. And so they're actually really well comparable. And here, there's still the problem that we can have a lower limit of spin echo times that we can reach. But to reach these shorter spin echo times, there's actually this, it was described first by Krautlow in 2016, the field subtraction coil. And with this field subtraction coil, we can subtract field integral. So we have still field along the entire setup, but if we want to go to lower fields, but we cannot, because otherwise we would lose the neutrons, we actually subtract field. And I told you that this spin echo times depends on the field times the length of the solenoid, which is what we usually call field integral. And if you make this negative, you can subtract field integral and can actually reach lower times. Now for resonant spin echo, as I said, we do this resonant flips using spin flippers and don't have the big solenoids anymore, but there's also limitation to lower fields. And so this is actually also a very good addition to a resonant spin echo setup. Now we can see here the example of RESEDA. This is the dynamic range of field integral and in the end spin echo times that we can reach without the field subtraction coil. You can see here at the right. And on the left, you can see what else we can access using our field subtraction coil. And you see those are several orders of magnitude. So this really is an extreme improvement for these resonant spin echo setups. So here's again the longitudinal resonant spin echo setup, as you can see it here at RESEDA. You can actually see here the spin flippers. You can see here in the middle these field subtraction coils, and you can see here these bigger coils that actually used to be bicycle wheels at some point that are our guide field. Now, these techniques are both very well suited to study, for example, soft matter, and you can really look at the dynamics of proteins and liquids. You can study the dynamics of water, for example. But what is difficult to do with both techniques, the classical NSE and the resonant spin echo, is actually to measure magnetism or with applying a magnetic field. And this is where the third technique I'm going to introduce now quickly comes in, which is the longitudinal MIEZE. MIEZE stands for modulation of intensity with zero effort, which, if you think about it, doesn't tell you all too much. But I will tell you here why, how MIEZE works. So we have, again, like with a resonant spin echo and a normal spin echo, polarized neutrons. We've used spin flippers to flip our spins. We have the subtraction coil, and until they actually come here, it looks pretty much the same as the first part of the resonant spin echo. But after that, we have this analyzer, and this analyzer we use to translate the phase that the neutron gathered into an intensity modulation. And after that, there's the sample and then only the detector. So we don't manipulate our spin anymore after the sample. And this makes it actually possible to measure magnetic samples, because otherwise, if you have a magnetic sample, the neutron spin will, of course, be sensitive to the magnetism and the beam will depolarize. But here we don't do any manipulation of the spin anymore, so we don't actually care if after the sample the beam is depolarized. So this actually works quite nicely in that case for magnetic fields, for depolarizing samples, and even for strong incoherent scatterers. As you might know, is that hydrogen is a huge incoherent scatterers, and in a lot of materials, of course, there's a lot of hydrogen, and if you have then that much incoherent scattering, you will have a loss of intensity, and you have to measure longer. So MIEZE is actually also rather nice for this. Now, here you can see the MIEZE setup at RESEDA. You can see this is exactly the first part is exactly the same. They actually kind of photoshopped the other arm out of here to get a nicer picture. And you can see here after the sample table, there's really just this tube, which we keep evacuated just so that the neutrons don't scatter on the air and we lose them. And there, this nice blue box is our detector. Now, I will sum up for you what are the pros and cons of NRSE and MIEZE. And I mean, you notice now that we have both at RESEDA, and why would you need both? So the NRSE is similar to the really classical spin echo. You can have very high resolution measurements. You can have very high momentum transfers, but you cannot use a magnetic field or magnetic samples, or rather it's very, very difficult to do so. And for strong incoherent scatterers, you will usually have to deuterate your sample. On the other hand, the MIEZE technique is similar more to a high resolution time of flight technique. You can use magnetic fields, you can measure ferromagnetic samples, and it's ideal for incoherent scattering. On the other hand, the resolution is of course reduced as compared to the classical spin echo. So you need to basically, if you want to measure one of these techniques, you need to think about, okay, what is my sample and what do I want? And so we actually strongly agree that it's good to have both options because they both just offer really different techniques. I showed you here a few pictures of spin echo setups. We have here first the classical NSE, which is the IN15 at the Institut Langevin in Grenoble. Then we have here the classical NSE with superconducting coils, as we have it in our neutron guide hole with the Jülich NSE. For the longitudinal resonant spin echo, we have the RESEDA, the arm 1 basically. And for the longitudinal MIEZE, we have RESEDA arm 2. Now, I guess most of you haven't heard about the MIEZE technique, and it's actually a rather new technique. But as we have learned in the last few years, is that there's a lot of interest worldwide because it is a really interesting technique to be able to measure dynamics in magnetic systems. And so we have actually collaborations going on with our colleagues at ISAS, at the LAMOR instrument, where they do a time of flight version of MIEZE. We have colleagues in Japan that are also doing a time of flight MIEZE. And in China at the Mianyang reactor, they're also planning on actually building a MIEZE, just as RESEDA is standing there basically. And the same is true for the PIC reactor in Russia. So people are really interested in the MIEZE technique, and which is really exciting for us because we have it already standing there. And at the moment, us and the colleagues in Japan are the only ones who have the MIEZE instrument really in user operation. So you've seen this picture already before as well. I actually took the liberty of removing the name of all the other instruments and just highlighting where in the neutron guide hole RESEDA is standing. And it's here right at the back. And as I said, there's the big suns right next to us. We're at the beam port number 5. We get cold neutrons. I think Astrid mentioned something, and also Anatoly mentioned about the temperature basically of neutrons as we define it. And cold neutrons have about a wavelength of 3.5 to 15 angstroms. The neutron guides are always slightly curved, which has the advantage that we do not get any gammas or other products that we would not want from the reactor itself. So this is, well, what RESEDA looks like if you want to really break it down in a very easy way. I will also go into a bit more detail on what these different things are, but I actually try to do this for like a challenge to how can you describe something really complicated in an easy way. And at RESEDA, we have like a box that picks the tiny things, which in our case are the neutrons, and how fast they go. Then we have things that flip the direction of the tiny things. We have things that make sure the tiny things don't get lost. We have the box that checks the direction. We have the position of things we want to study. We have an air-free box, and we have a picture-taking box. Now in a bit more detail and a bit more sophisticated words, we have actually the same one as the suns. We have here the velocity selector. And we don't actually select one wavelength like you would do, for example, for triple axis. We can actually, one advantage really of these neutron spin echo techniques is that you can take a wavelength band. So we actually take plus minus 15% around the wavelength that we choose, which gives us many more neutrons and which reduces our measuring time quite a bit. And as I said, we have a polarizer. We have slits because sometimes we want to just have a bit more collimated beam. If you do SANS applications, as Sebastian told you, there's you need a very nice and collimated beam, and it's good to already start right in the front. Then we have our resonant spin flippers. We have the transmission bender, which is our analyzer here, which we take out when we don't use the MIEZE technique, but we only use the resonant spin echo technique. And yeah, we have our sample table, which is here. And for MIEZE, we have just the evacuated flight tube and the detector. And for the NRSA, we have the symmetrical setup as we have on the basic arm, just with the magnetic field flipped. And then we have another detector here. What is a bit sad is that the resonant spin flippers actually limit the size of our beam a bit, which also means that our detector is a bit smaller. That means for NRSE, we actually have to count longer than the people doing classical NSE because they have bigger coils, so they can have a bigger detector as well. But I guess it's a trade-off we have to live with. Now, you might wonder, okay, what can you do with RESEDA or with spin echo or MIEZE setup in general? With the NRSE, you can do anything you can measure with NSE with the limitations that I mentioned. With MIEZE, you can actually do some inelastic measurements, and I will not go into detail in this because it's rather complex and we don't have that much time. You can do strong incoherent descattering samples, and what we do actually a lot lately, and where we have actually a BMBF project running to optimize RESEDA for this, is MIEZE SANS, which is excellent for ferromagnets, which I'm going to talk about in Skyrmions, as well as superconductors and magnetic nanoparticles. So my first examples is the fluctuation at the Curie point in iron. And as I said, I'm actually quite happy that Astrid already talked about the iron, so you already know the basics about the iron. And yeah, so this is actually a project by a former PhD student, Stefan Seubert. So first of all, we need to know where exactly is the Curie point in iron, because of course there might always be a small temperature offset with the oven that we use, or not all samples at exactly the same TC. So what we first do is we really check, and you can actually see that very nicely if you just plot the intensity versus the temperature. You see that there's a peak here at the scattered neutrons, which is our TC. But if you look at the transmission, which you can see is it's 3 orders of magnitudes less, there's a critical opalescence actually happening here. These are quite interesting phenomena, but these 2 points give us actually a really nice opportunity to determine the TC of iron very well. Once we know exactly where our TC is, we're going to scan around the TC. And now here I plotted the data as we get it in at RESEDA, which is like the S of Q and tau. So we're in function of a time for the normal spin echo. It's the spin echo time for us. It's a MIEZE time because it's definition is slightly different, but basically they correspond to each other. And on the panel below, I plotted the S of Q and delta energy, which is what most people are familiar with and which you have also seen in Astrid's talk. So we started our measurement at slightly above TC. So we're at TC plus 10 Kelvin. And you can see here, we have here an exponential decay, which gives us basically a lifetime and a line width. And here we also have this Laurentian peak, which also gives us a line width for this excitation. So this is rather what we would expect. But as we go closer to this TC, so now we're at basically in the non-ferromagnetic state, and we're going down towards the ferromagnetic state. We have the time, you can see here, goes to higher times here. And this means actually that our fluctuation, the lifetime of our fluctuation becomes longer. Now, what does that mean? So if we go closer to the transition temperature, there will be bigger patches of ordered spin already, because the closer we get to the Curie temperature, the more ordered the spins will get. And at the Curie temperature, we have this perfectly ordered ferromagnet. These bigger patches of spins, which will still already be ferromagnetic, will fluctuate at slower times than they would if we go to higher temperatures. And you can see that this is true even if we go to TC plus 1. And after that, we actually go to below TC and watch what happens close to the Curie temperature if we are in ferromagnetic states. And you can see that the shape of our curves completely changed. You can see here that in the S of Q and tau, we have not just an exponential decay anymore, but we have this oscillation, which is a clear indicator for an inelastic signal. And if we look at S of Q and delta E, we have the same thing. They have the signature for a inelastic signal, which is basically two peaks at a finite energy, but a quasi-elastic peak usually centered around zero energy. As we go now to lower temperatures, you can see that the oscillation of the period actually goes down as we go down in temperature. And that actually means that if we would go the other way around, so if we go back here, the oscillation period becomes longer, sorry. And that actually shows us that our spin waves, because that's what we get the signal from, or magnons, they're actually softening as they reach the transition temperature. And we went to even lower temperatures, down to TC minus 20K, and you can see that this oscillation just becomes, has a shorter and shorter period. And if we now plot the line width that we get above TC as a function of Q, so as a function of the scattering vector that we look at, we see that this doesn't perfectly depend, it's not perfectly Q square dependent. And that actually means that we have not just these ferromagnetic interactions that are going on here and paramagnetic fluctuations, but there's also some diamagnetic fluctuations happening, which is actually really, really interesting. Now, the next project I'm going to talk about is from our previous co-worker, Jonas Kindervater, and it's about Skyrmions. And this is actually a work that we did together with Sebastian Mühlbauer from SANS. So you will also see some SANS data again to just close the circle again. So I want to quickly repeat the phase diagram of manganese silicon, which is the material that was studied here. And you can see it's already rather complicated. We have at high fields and high temperatures, we have a field polarized phase. Then we have a conical magnetic structure, a helical magnetic structure, and we have paramagnetisms at high temperatures and high fields. And then there is this pocket, this red pocket here, which has long not been, well, there have a lot of things have been predicted for this, which was used to be called the A phase, until actually at the MLZ, they discovered that that's where the Skyrmions sit in this phase diagram. Yeah, I've made a zoom in here so that you can see that. And in this project that I'm telling you about now, is actually they studied this phase transition from the Skyrmion lattice to the paramagnetic phase and back, because they wanted to know, okay, how do these Skyrmions build from the paramagnetic phase? And for this, the researchers started with SANS measurements. So these are now pictures from SANS 1. And you can see here this beautiful six-fold pattern, which is basically the signature for Skyrmions. And you, well, if you would use a ruler now, you could see that there's exactly 60 degrees in between. And if we go to the paramagnetic field phase, so if we here, this was done by actually just increasing the temperature a bit, you can see there's just this diffuse ring of, well, not very much happening. And what they found in between is that you have a superposition of the both. So you have already this six-fold pattern, but on the other hand, you have underneath this diffuse scattering. So that seemed rather interesting. So everyone wanted to prove, okay, this is not some static remnants of the Skyrmion lattice, but this is fluctuating. So this is basically, so the idea was that the Skyrmions in this phase in between paramagnetism and Skyrmion phase, they're kind of fluctuating. You have like a Skyrmion here popping up and it decays again and popping up there and decays again. It's like, the idea behind it is like there's similar to when you freeze water, right? I mean, if you go from high temperature to low temperature, you will have these crystallines building in water that will melt again and build up again and melt again until your temperature is so low that the entire thing will freeze. Now, to actually prove that this is really dynamic and not static, we went from SANS to RESEDA. And you can see here that, well, our detector is a bit smaller and a bit closer than the one at SANS, so we cannot see all the nice Skyrmion peaks at our detector, but you can clearly see that they're there. And we can actually move our arm around a bit so we can make sure they're all there. And then we measure the intermediate scattering function as a function of different temperatures, and we measured it in 2 different field directions. And you can see here that this is the high temperature. No, wait, the other way around. This is the low temperature phase where we have our static Skyrmions. Then you see that there is actually a decay. So there's something happening. There's something that moves on this time scale. And when we go to higher temperatures, you can still see, oh, this is still moving, and it's moving actually, it's fluctuating faster the higher temperatures we reach. And we actually found that the lifetime of these Skyrmion precursors here are at around 1 nanosecond. So that was pretty cool, and that was actually something really nice to figure out on how these Skyrmions build up from the paramagnetic phase. And with that, I think I'm pretty good in time. And well, as Sebastian also mentioned, and I guess as everyone knows, measuring at an instrument like this and keeping an instrument like RESEDA running requires quite a lot of people. And I have been an instrument scientist at RESEDA now for a bit more than 2 years. And Chris, who was there before me and who really worked very hard at getting RESEDA running properly, has now switched to Panda actually, and is working with Astrid, and will later move on to Topaz. And I have since like a month, I have a new colleague who joined me at RESEDA. They have a postdoc who was applied on this BMBF project where we want to actually optimize RESEDA for SANS measurements. We have professors, of course, supporting us. Then we have excellent technical support by our technician, Christian Fuchs. We have 2 PhD students that are kind of working a lot at RESEDA, which are Franz and Andreas. And then we have 2 more students that are, well, Peter just did his bachelor thesis, but they're basically working students at RESEDA, Peter and Lucas. And actually, in the middle of this month, Xava, who has already asked a few questions today, has joined us as well. So we're always a growing team. And yeah, with that, I would like to ask you, I would like to thank you for your attention, not ask you for your attention. And yeah, if you have any questions, feel free to ask.